So in the last two videos, we went over representing geometry as pure mathematical equations, and they work. The way we get intersections is literally by expanding by expanding the equations and integrating by stubbing into the point, by stubbing our parametric array equation into the mathematical equation for our shapes. So remember what we did for sphere. We had the equation which is any point p dot p equals radius squared, right? And for plane we had p dot normal equals 0. And we could tell from what we did last time, there was a lot of effort going to obtaining the analytical solution for the intersection test, and that is not always, it's really tiresome, and you don't really have a good way to model complex geometry with mathematics in an easier way. So from now on, we will switch to in my opinion, way more powerful representation of 3D geometries. So instead of pure mathematical equations, there's another construct that we can use. It's called distance functions. And ideally, they'll be signed distance functions. Signed. And sometimes they're called distance estimators. These are cases when the actual distance function cannot be obtained. One of the perks of being at UCSD is that you can hear stuff like this occasionally, right? So there's also stuff called distance estimators. There are functions for estimating distance when distance function derivation itself is not possible. So when you see words like SDF, standard distance function, DF, or DE, distance estimator, these are pretty much in the same category in that they use in order to ray trace these geometries under this kind of representation. There's a technique called ray matching. We'll talk about ray matching does. Before that, let's first try to formalize the idea of signed distance function. For right now, let me just call this function SDF. It takes in an x component, a y component, a z component, and returns a scalar. You know, it's not piecewise, but the indication of the result is piecewise. So if it's a positive number, if it's a negative number, and it's 0. I'll talk about the meaning. If the result of this function is positive, then it's the distance from the geometry's surface to the point with the coordinate x, y, z. Conversely, if it's negative, then it's also, if you negate the value, then it's also the distance between the surface. Well, what's the difference? The difference is that if the result is positive, then that means the point is outside of the surface. If it's negative, then the point is inside the surface. So if the distance function is signed, then you can represent the kind of the volume of the geometry. You kind of have a distinction between inside and outside. And if it's 0, that means the distance to the surface is 0, which means that it's on the surface. This type of surface is called isosurface. It's also what you would call as implicit geometry, because they're not explicitly defined. Instead, they're modeled by distance functions. So why are they so useful? Now imagine we have some magical sine distance function that represents our scene by following the desired results, by following the rule of a sine distance function. So we have say we have a sphere in the scene and we have a plane right underneath the sphere, and this is our camera. And we're shooting out a ray to see where it intersects. Well, we can start at t equal to 0, right? So when t equal to 0, the point at which t equals 0, the first thing we'll do is we compute the sine distance from this current point to any surface in the scene, so any geometry in the scene. Now, the distance we obtain is this, right? It's not going to be, usually it's not going to, we're not going to reach the distance instantly, which we usually have some other obstacles in the way. So remember, we have enclosed, if we obtain the sine distance of the current point to any geometries in the scene, we basically have obtained a sphere of which that within the sphere there's no surface or geometry in the way, right? So it is safe to travel to anywhere in the sphere and not worry about overshooting, i.e. you miss the intersection. Like if I just do constant stepping, I could have just missed it or just landed on an incorrect result. By taking the sine distance function, we can safely, move to a point that we know will either be on the surface or outside of the surface. Then after one step of iteration, we just keep computing the distance. In this case, it will be, right on the surface. Next step, we have reached the surface. This is quite an optimistic case, the representation of the problem that we're doing. Usually, if you have a small crease, then you can imagine it will be really slow. It'll take many iterations to get out of the crease just to get out of it. So that's kind of a downside, right? But when the ray or when the point that we're testing has a SDF of 0, that means we're basically on the surface due to the definition of sine distance. So that is really convenient. But usually you don't want to test it against 0 per se, because imagine this case where the ray literally grazes by surface. Well, what do you do? You can imagine first we test the sphere when we slowly enclosing in. As we approach this grazing angle, the sphere gets smaller and smaller, but it almost is never going to reach its destination because there's always a little bit of gap between each sphere to the actual destination. Well, what do we do in this case is that instead of testing the SDF of the current point with 0, we test if it's small enough, or in this case, let it be more mathematical. If it's smaller than epsilon, which is a value which is a small value, if this is the case, that means P is either inside or right on some surface. And that is what we're going to do. So that's the basic idea of distance functions and ray matching. What distance estimator, the difference it makes for distance estimator is that it's the same function basically, but it does not guarantee that you will obtain the upper bound. So if the ray is here, instead of obtaining the absolute maximum distance you can travel, what you do is it gives you some distance, but it's not guaranteed to be the maximum distance to the scene, and instead, but one characteristic it has to have is it has to be the lower bound of the scene. So you cannot have a sphere that's bigger than the actual distance. As long as the distance estimator does not overstep and it's continuously progressing, then there's not really a problem. But such distance estimator also works for our simple array marching scheme. Why is that so useful though? Why is signed distance function such a better representation of geometry than just mathematical equations? That is because before we feed the point into signed distance function, we can do some modifications of p. Let's say p assigned to some functions of p. You can imagine you can pull space, you can kind of modulate the space right on the surface. That way you can achieve a large variety of complexities. And because some shapes are inherently not, they come from chaotic systems, so fractals, they can only be ray traced either by constantly staffed ray marching or obtaining a distance estimator for them and therefore ray march them. There is not a solid mathematical equation, partially due to the reason that they come from a chaotic system. The derivatives on any surface is not obtainable. It's, undefined because they have infinite details. Or examples like super shapes, which have equations in the form of latitude and longitude, which you could easily convert the point in the latitude or longitude form, then compare the distance. In this case, it's not going to be the absolute distance, since if we're in a crease and points here, the actual closest distance is probably something like d1, but the actual distance d1 plus some small value, then you'll be overstepping. We'll talk about this case when we come across it, but for now, let's forget about it. Let's focus on signed distance function, which is what we'll be doing. Now remember, we had a sphere and a plane last time. I want to represent the same geometry by using signed distance function. How do you do that? Well, if we reduce this down to a 2D case, you have a sphere that's centered at the origin, and you have a random point P. What is the distance between the point to the circle? Well, isn't it just the length of P, which is P subtracted by origin difference vector? Isn't this just the length of this vector subtracted by the inner radius of the sphere? Right? So SDF P is really, you take the length of P subtracted by R. And obviously, it should be clear that this equation also extends itself nicely to the sphere, since the definition of circle extends the sphere by just adding one more dimension to it. It becomes a 3D sphere very naturally. And if the point is inside a sphere, then you will be subtracting a bigger value from a smaller value, then that will be negative. So we took care of the sign aspect of it, and when the point is right on the surface of the sphere, it gives a 0. Right? What do we do with the plane? Well, that's even easier, because remember we had a ground plane with normal going up. All we have to do is to test the y component of the p. So literally, we just take the y component of it. If you want to do ray tracing from underneath the plane, you could just take the absolute value of it, right? So it'll be the absolute value of p dot y. Now you can obviously see that instead of trying to solve a mathematical equation, we can literally just represent the geometry with these signed distance functions, and combined with the technique of ray marching, the intersection test will become much easier to solve, and there will be less room for error. But do beware that because of what I talked about, there is going to be a tolerance error involved, so your result is not going to be exactly right. I copied the camera model into a new shader. So why don't we define the SDF, which is the scene. This time it's just going to be a sphere. Okay. Alright, I have not talked about combining how do we combine the signed distance function between a sphere and plane, since we need some new sign distance function that encompass both the sphere and the plane. So it will give us the maximum distance to both the sphere and the plane at the same time. Well, guess what? All you have to do is to take the minimum of the SDF of sphere and SDF of plane. Why does this work? Well, remember what we talked about. The point of sign distance function is to compute the maximum distance from the point to the scene. So say our point is here. This is our point. We first obtain the sign distance from the point to the sphere, d1. Then we obtain the distance to the plane, d2. Which d do you choose? Well, it turned out you always want to pick the one that's smaller, because if the bigger one has an impact, then you will be overshooting it, right? Take the minimum of the sign distance functions from all the geometries in the scene. This way you only reach the minimum distance to any geometry while retaining the property that these distances are going to be the maximum distance to the geometry. Alright. So just like last time, we're going to write an intersect routine, well, which in this case we're going to be R0, or origin, excuse me, ray direction, right? And learn from our lessons, we know that we probably need a material index so that we can test both sphere and the ray. Alright, I'll show you how much easier it is. Okay, so we start at some point, so t starts at 0. Remember, our ray tracing is an iterative process. We'll have some sign distance function representation of the function. We don't actually know where they are. We don't have the analytical solution for that. All we do is to first place t as some value, then find a maximum distance, add that to the t. So the sign distance function of the first iteration, sign distance function of the second iteration, so on, until t reaches the epsilon threshold, meaning that the current point being tested is close enough to the surface, and at that point we can use it as the intersection point. Or we can just take out t. Again, it's such a convenient notation that because we can use t as both the distance and use it to derive the position from the parametric ray equation. Alright, so float t starts from t. Let me just loop something for a finite amount of times, right? Then I'm going to define a new function called SDF, which take a 3D vector. If it's just a sphere, the sphere SDF is just length minus the radius of the sphere, in which case we're going to make this 1.0, which is what we had. And the floor SDF is going to be p dot y, and we're going to take the absolute value of it just to be safe. One more thing I'm going to do is to, not make the same mistake I made last time. First, modify the camera to be looking at it from a good perspective. And remember what I said. Since this is the sign distance function, we kind of already need to extract the materials of the closest point, because that's when we determine what objects we hit. So mat ID, if sphere SDF is smaller than SDF, floor SDF, that means we're going to take the sphere's distance, so return sphere SDF, and right before returning, we're going to assign the material index to 1, which is similar to last time, and else the floor SDF is going to be closer, and mat ID is equal to 0, and return the floor SDF instead. I'm thinking about a more convenient way of doing stuff. For example, if you have a shit ton of SDFs, how do you actually, you're not gonna do this every time because it's error. See, I already made an error here. You're supposed to return the plain SDF. But another way we can do stuff is just kind of separate the material assignment and the sphere SDD assignment. We first assign the minimum SDF to the scene SDF, so floor SDF, and then compare the result SDF with the sphere SDF. So if the actual result SDF is smaller than sphere SDF, we assign the material index to 1. Otherwise, really we could just do equal, since the minimum doesn't actually. We don't have to care about the floating point precision problem here because we're literally just doing an if statement assigning, literally copying the bits to the SDF value. So if sphere SDF actually matches the SDF, then there's no discrepancies caused by the precision issues. So that's going to be our SDF function. And what we have to do now is first create a mat index outside so we don't lose it after we finish looping. And when we're going to call the distance d, we want to find the distance of the current point, which is ray origin plus t times ray direction. Remember, this is the parametric equation for the ray form. And this is the point that we're being tested, and mat ID, which is the material index we want to retrieve. And if this distance is smaller than a certain value, which in this case I'm just going to make it 0.001, we're going to actually, let me make a different name. Current mat ID. We don't want to assign the material index to the result material index before we know that the point has been close enough, right? So instead we're going to have -1 denoting that there's no intersection happening, even though in this case it's not really possible. But if it intersects, we want to break out, and before we're breaking it out, we want to assign the current material index to the actual material index of intersection. Otherwise, if it does not get close enough to the surface, we just add distance to the t, kind of marching along the ray until we hit something. Mat ID redefinition. Alright, so we already have that. That's great. We can just assign it then to -1 just to be sure, and return t, something like that. And all we have to do is make a mat ID that retrieves it, and the distance, well, in this case it will be the t intersection of ray origin, ray direction, and mat ID. If mat ID is not equal to -1, which means we've hit something, then we assign the y to color, and before we do that, we need to declare the color in front above it. So let's do that. We indent this, and there we go. Remember we're looking too high up, so we can kind of see some artifacts due to the epsilon threshold that I talked about. That we can kind of counter that by tweaking it a little bit. Again, we can do the same thing with our materials. So if mat ID equals 0, we assign y to the plane, and if it's not, that means we've hit the sphere and want to give red to the sphere. It's the exact same thing that we did last time. And look at how much simpler the intersection routine is. And remember what I said, something that you can do with the sign distance function is that you can modulate the distance quite easily. So this is sphere SDF. I could simply do sphere SDF equals, plus the sign of p dot x. You see that? The change is made instantly. You can experiment with different kind of math to test what will happen to this thing if you do stuff like that. So p dot x, it's pretty obvious. P dot x, if it's negative or positive, actually it's not quite obvious, but if p dot x is equal to 0, sine of 0 will equal to 0. Yeah. So if p dot x whatever. You can try to think about yourself. We can do p dot x, p dot y. Already some really weird shape happening, which I think is pretty cool. One of the neat properties of, you know, being able to pretty much assign distance function represent the geometries. So you can feel free to do experimentations on your own, right? And one last thing is you really have to watch out the number of steps you're stepping, or is it the intersection? One of the tricks that I want to share with you is that you can monitor how well you're doing. Actually, let me pull this out. There's really no reason this should be in here. So let me just, well, whatever. I'm just gonna keep it. I guess we'll leave what I want to say to the last video. So this is it. You can see, you know, compared to, let me just take out our analytical code. This is our intersect routine, right? And there, it's very hard to change. I want to change some number. 3. I don't actually know. See, it's very hard to expect what the change will actually do. But you know, assign distance function case, you know, most of the code that we see here are just material lookup, and the actual intersection routine never changes. The only thing you have to change is the sphere SDF. In contrast with the analytical solution, where the bulk of the code is literally doing the analytical intersection test. So this is why I think ray matching is a way more superior method. It allows for much freedom of manipulating the 3D geometries instead of have to, you know, go back to the paper every time you have a new geometry you want to add to the scene. So that's it.